The rule of thumb of 1 kilowatt per horsepower is a reasonable approximation for estimating transformer size needed for submersible motors. However, consider the motor's specific characteristics and operating conditions. For a 40 horsepower motor, the load is approximately 40 kilowatts. For a 50 horsepower motor, the load is approximately 50 kilowatts. An existing 45 kilovolt ampere transformer translates to 45 times 1.732, which is about 78 kilowatts, assuming a three-phase system. If the power company claims a 300% loading capacity, this suggests 78 kilowatts times 3, equaling 234 kilowatts. Given that the existing transformer has a capacity of 78 kilowatts, it appears sufficient for the 40 horsepower motor load. Applying the 1 kilowatt per horsepower rule, a 50 horsepower motor requires about 50 kilowatts. Considering the power company's claim of a 300% loading capacity, this yields a potential capacity of 234 kilowatts. Based on this analysis, the existing 45 kilovolt ampere transformer might suffice for the 50 horsepower motor, especially if the power company's assertion of a 300% loading capacity is accurate. The claimed 300% loading capacity is quite unusual. Most transformers are designed for a maximum load of 100% or 125%. Operating a transformer continuously at or beyond its rated capacity can shorten its lifespan and elevate the risk of failure. If the motor fails due to undervoltage, retrieving it from a depth of 300 feet could be challenging and expensive. Consider potential future loads on the transformer. Ensure the transformer provides adequate voltage regulation to maintain motor performance. Implement suitable motor protection mechanisms to prevent damage from undervoltage or electrical faults. Consult the transformer manufacturer to verify its actual loading capacity and obtain their recommendations regarding the suitability of the existing transformer for the 50 horsepower motor load. When assessing transformer size for submersible motors, it's crucial to delve into several key considerations beyond the simple 1 kilowatt per horsepower rule of thumb. Firstly, understanding the specific motor characteristics is paramount. Factors such as the motor's service factor, starting current, and efficiency play significant roles in determining the actual load the transformer will experience. Motors with higher service factors can handle overload conditions for short periods, but this also means they may draw more current during normal operation. The starting current, often several times the full load current, places a significant burden on the transformer during motor startup. A motor's efficiency dictates how much electrical power is converted into mechanical power, with lower efficiency resulting in high power draw from the transformer. Secondly, transformer capacity must be carefully evaluated. The kilovolt ampere rating of the transformer indicates its apparent power capacity, which is the vector sum of the real power in kilowatts and the reactive power in kilovars. For motor loads, reactive power is particularly important as it is associated with the magnetic fields required for motor operation. A transformer's ability to supply both real and reactive power determines its suitability for the application. The power company's claim of a 300% loading capacity should be treated with skepticism. Standard transformers are typically designed to operate continuously at their rated kilovolt ampere capacity, with limited short-term overload capabilities. Exceeding the rated capacity can lead to overheating, insulation breakdown, and ultimately transformer failure. It's essential to verify the transformer's actual overload capacity with the manufacturer and understand the potential consequences of operating beyond its design limits. Thirdly, voltage regulation is a critical factor in motor performance and longevity. Voltage drop occurs as current flows through the transformer and the electrical distribution system. Excessive voltage drop can cause the motor to operate inefficiently, overheat, and potentially fail prematurely. Transformers with good voltage regulation maintain a stable output voltage under varying load conditions, ensuring that the motor receives the required voltage for optimal operation. Fourthly, motor protection is essential to prevent damage from electrical faults and abnormal operating conditions. Undervoltage protection is particularly important for submersible motors, as low voltage can cause the motor to draw excessive current, leading to overheating and insulation damage. Overcurrent protection, such as fuses or circuit breakers, protects the motor from short circuits and overloads. Ground fault protection detects and interrupts ground faults, preventing electrical shock hazards and equipment damage. Fifthly, future load considerations should not be overlooked. If there is a possibility of adding additional loads to the transformer in the future, it's prudent to select a transformer with sufficient capacity to accommodate these loads. Oversizing the transformer slightly can provide a buffer for future expansion and prevent the need for costly upgrades later on. Finally, consulting with the transformer manufacturer is highly recommended. The manufacturer can provide valuable insights into the transformer's capabilities, limitations, and recommended operating conditions. They can also help assess the suitability of the existing transformer for the new 50 horsepower motor and provide guidance on selecting a replacement transformer if necessary. When evaluating the suitability of a transformer for a submersible motor application, it's important to consider the various starting factors that could affect its capacity. Starting factors are adjustments made to the transformer's rated kilovolt-ampere capacity to account for specific operating conditions or environmental factors. Altitude is one starting factor to consider. At higher altitudes, the air is less dense, which reduces the transformer's ability to dissipate heat. This can lead to overheating and reduced lifespan. Transformers installed at altitudes above 3,300 feet above sea level typically require derriting. Ambient temperature is another important consideration. Transformers are designed to operate within a specific temperature range, typically up to 104 degrees Fahrenheit. Operating the transformer at higher ambient temperatures can reduce its lifespan and increase the risk of failure. Derriting may be required for transformers installed in hot environments. Harmonics are also a factor. Nonlinear loads, such as variable frequency drives often used with submersible motors, can generate harmonic currents that flow through the transformer. These harmonic currents can cause additional heating and voltage distortion, which can reduce the transformer's capacity and lifespan. Transformers supplying nonlinear loads may require derriting or the use of harmonic filters. The type of cooling used by the transformer also affects its capacity. Transformers can be cooled by various methods, including natural air convection, forced air cooling, and oil immersion with radiators. Each cooling method has a different heat dissipation capability, which affects the transformer's allowable loading. Transformers with less effective cooling may require derriting. The insulation class of the transformer determines its maximum operating temperature. Transformers with higher insulation classes can withstand high temperatures without degradation. However, even with a high insulation class, it's still important to avoid exceeding the transformer's rated temperature to maximize its lifespan. The impedance of the transformer affects its voltage regulation and short-circuit current. Lower impedance transformers provide better voltage regulation but also have higher short-circuit currents. Higher impedance transformers have poorer voltage regulation but lower short-circuit currents. The appropriate impedance level depends on a specific application and the characteristics of the electrical distribution system. It is crucial to take into account the submersible motor's starting characteristics when determining the appropriate transformer size. Submersible motors typically have high starting currents, which can cause significant voltage dips in the electrical system. The transformer must be sized to accommodate these starting currents without causing excessive voltage drop, which can prevent the motor from starting or damage other equipment. To mitigate the impact of high starting currents, several techniques can be employed, including reduced voltage starting, part winding starting, and the use of soft starters. Reduced voltage starting methods, such as autotransformers or reactors, reduce the voltage applied to the motor during startup, thereby reducing the starting current. Part winding starting involves energizing only a portion of the motor windings during startup, which also reduces the starting current. Soft starters use solid-state devices to gradually increase the voltage applied to the motor, providing a smooth and controlled start. In addition to considering the transformer's capacity and directing factors, it's also important to ensure that the transformer is properly protected against overcurrents and short circuits. Overcurrent protection devices such as fuses or circuit breakers should be sized to protect the transformer from overload conditions while allowing for the motor's starting current. Short circuit protection devices should be sized to quickly interrupt fault currents, preventing damage to the transformer and other equipment. Regular maintenance is essential to ensure the reliable operation of the transformer. Maintenance tasks should include visual inspections, infrared scanning, oil testing, and insulation resistance testing. Visual inspections can identify signs of damage or deterioration such as leaks, corrosion, or overheating. Infrared scanning can detect hot spots, which may indicate loose connections or insulation problems. Oil testing can assess the condition of the transformer oil, including its dielectric strength, acidity, and moisture content. Insulation resistance testing can measure the integrity of the transformer's insulation. The power company's suggestion that the transformer can be loaded to 300% of its rated capacity is highly unusual and should be viewed with extreme caution. Operating a transformer at such a high overload level can significantly reduce its lifespan and increase the risk of failure. It's essential to verify the transformer's actual overload capacity with the manufacturer and understand the potential consequences of exceeding its design limits. If the existing transformer is not adequate for the new 50 horsepower motor, it may be necessary to replace it with a larger transformer. The size of the replacement transformer should be based on a comprehensive load calculation that takes into account all of the factors discussed above, including the motor's characteristics, directing factors, and future load considerations. Selecting the appropriate transformer size for a submersible motor application requires careful consideration of various factors. It's crucial to go beyond the simple 1 kW per horsepower rule of thumb and delve into the specific characteristics of the motor, the transformer's capacity and directing factors, voltage regulation requirements, motor protection needs, and future load considerations. Consulting with the transformer manufacturer and a qualified electrical engineer is highly recommended to ensure that the selected transformer is adequate for the application and will provide reliable and safe operation. Consider the effect of running the motor with a variable frequency drive. The use of a VFD will change the calculations needed for transformer size. Additionally, the harmonics created by the VFD need to be considered. The 300% load in the utility suggested is likely a short-term overload rating that has safety margins calculated for a short period of time. This does not mean the transformer can continuously supply this much power.